Okay, so last time we had started on time synchronization, and I was going through different ways where, or different applications it might be useful. Um, so I looked at localization as an example. The one which I'm going to start today is medium access control protocols, which has been a very key driver of time synchronization. So medium access control refers to the fact that anytime you have some shared communication medium and you have multiple transmitters which want to transmit over it, send it to each other, then very broadly two categories of schemes. One where you sense the channel, see if it is free, and then go ahead and transmit. And if you are wrong, there will be a collision, but so some sort of a channel sense mechanism is how it works. And classically, things like Ethernet and related protocols have operated that way. The problem with that is, of course, collision, and under heavy load conditions, the actual throughput of the channel can go down. So the other category of techniques which have forever been around are the ones which are based on some sort of coordination in time. So kind of the idea is that nodes maintain the shared concept of time, and then we divide time into slots and then give transmission privileges through some sort of a schedule. Now, under lightly loaded conditions, the overhead of doing this synchronization and all is not worth it. And also it's more rigid because once you assign a time slot to someone, whether it uses it or not, it goes waste. On the other hand, if you have traffic which is very sensitive to time, you want to offer it some deterministic delay or some guaranteed throughput, then that scheme works. So modern MAC protocols, the type you see in Wi-Fi, for example, are kind of a hybrid. So the way, at least a full standard of Wi-Fi, what it supports is the concept that every so often there is a period of time in which things switch to some sort of a guaranteed transmission mode, guaranteed rate, and at other times it does that, sense the channel and transmit. Okay, so to make that magic happen, nodes need to know time. And in case of Wi-Fi, the way it works is that your access point once in a while transmits a beacon, which is on a periodic basis, and at that time everyone else syncs up. So essentially, every so often, access point is conceptually saying time at my end is this. Okay, it announces the time, and then others can sync up to it. Okay, so throughput or avoiding collision had been one reason why time-oriented schemes, so guaranteed throughput, guaranteed delay. Another reason is power. So the very same collision which affect the throughput are also a wastage of power. And there are a couple of things which happen there. So one is that if you collide, then your effort at transmitting the packet has gone waste. But the other is, think from the receiver's perspective, since there is no prior agreement as to when the transmitter is going to send. So traditionally in those protocols, the way receivers work is they stay up. They stay up waiting for a packet to arrive. And that is fine as long as receiving a packet is very low cost relative to transmitting a packet. And that's true for very long range radios, cellular radio, satellite transmission, things like that. But it's not true for short range radios. So in short range radios, since you don't need that much energy to transmit, so the energy to receive begins to dominate, and in fact can be much higher than the energy to transmit. So now if your receiver has to stay up, then the approach of just transmitting at arbitrary point of time and receiver staying up is going to be less good from an energy perspective. So starting around, let's say in the recent dozen years or so, as short-range wireless techniques became quite prevalent because of sensors and stuff like that. There's been a lot of work towards MAC protocols which are optimized for power instead. And part of, so there are two, radio people have tried to make radios very efficient in terms of receiving, but other part is we organize MAC protocols in a manner where we minimize how much time the receiver has to stay up for. So in that vein, so we'll see that the role that time ends up playing. So the issue that boils down to is that the receiver doesn't know when the transmitter is going to transmit, then of course it has to just stay up. Or the other alternative is that the receiver can come up at random times and hope that the transmitter happens to transmit at that time. It doesn't really work out. But even when receiver knows when the transmitter is going to transmit, the problem is that they would have synchronized sometime in the past. So if two radios agreed that at some time t they are going to exchange a packet, one is going to transmit a packet to the other, the problem that happens is that because of clock drift and also any offset error in synchronizing upfront, the combination of the two means that when one node says, hey, by my local clock it's time t, and when the transmitter says the same thing, they're going to be somewhat, they're not going to be identical. So for example, if we take a 10 ppm crystal oscillator, and let's say this is some very ultra low duty cycle type system, so maybe we are going to connect back to the transmitter once a day just to do a reporting. Transmitter is going to connect. So 86,400 seconds, we are drifting 10 microsecond, 10 ppm, so 10 microsecond every second. So over 86,400 seconds, that would be 0.8 seconds. So roughly a second apart, we would end up being at the end. What that means is that the receiver has to budget for that. It has to wake up beforehand, and in the worst case, it may actually stay up as much as twice that because the transmitter may have erred on the other side. So that's what the slide is showing, that the receiver has to now provide a guard then to budget for this error in the initial synchronization as well as the subsequent drift that has happened due to the clock frequencies not being the same and then subsequent also drifting apart. So the goal then becomes, is there a way we can optimize for this as well? Are there ways in which we can reduce this overhead also? So let's look at how it plays out. Now, an additional complication which comes up is that many of these systems, particularly sensors, they duty cycle. And what I mean by that is they shut down, and then only when something interesting happens, they may be sending things out. So for example, let's imagine you have a system to monitor some sort of a target. Okay, I've shown a little animal, but just imagine some sort of an event that you are observing. That event can happen at any time, and usually you would have some sort of a constraint in terms of how soon the backend should get to know it. So conceptually, the way the system might work is that your sensor would sample for the event. So the sensor would be sampled to collect enough samples so that you can make a decision: is the target there or not? And then since the target does not, target has some level of persistence, like if you're observing some section of, let's say, a road, the target may take some amount of time to go through it, so you don't have to remain up constantly. So quite likely what you may be able to do is look at the channel, nothing there, go back to sleep, again look at the channel, nothing there, go back to sleep. So the top line is showing that every so often the sensor node wakes up, collects some samples, presumably does some signal processing, some event detection, some classification, regression, those kind of stuff, decides that is there an event, and if so, then it sends out a report. So most of the time there is probably no event, so the sensor wakes up, finds nothing, goes back to sleep. But once in a blue moon, the event is there, then it actually has to send things out. So the scenario now is that the node is transmitting once in a while at unpredictable times. Now, the way the radios work out is, and this is the point I was making a little bit earlier, that at short ranges, the power story changes significantly from the way it works at long ranges. So if you look at radios, or for that matter, any communication system, There are really kind of three pieces that exist out there. There is electronics on either side, and by that I mean things which are running your protocol, which are doing modulation, demodulation, things like that. And then there is some sort of an amplifier which pumps out the energy, which goes over the wireless channel or your cable or whatever. And for reception to be successful, you need to be able to receive the signal with adequate signal to noise ratio. And what that means is that the transmitter should be transmitting with adequate power, which basically means that the amplifier should be pumping out enough energy. So at long ranges, or very cluttered environment, the amplifier has to pump out a lot of energy just so that reception can take place, and therefore this energy dominates. So if you look at, let's say, a cellular radio or even Wi-Fi radios, they dominate. So on the right-hand side, I've shown it only for a short-range radio, but I'm showing it for the amplifier, the green stuff. The transmit side electronics, this is where your MAC protocol, Q buffers, those kind of things are taking place, modulation, and then the receive electronics where the counter part is taking place, demodulation, things like that. So in long range stuff, the RF dominates by far. If you are in, like when you hear, when TV stations or radio stations in our cities transmit, they transmit at kilowatts of power, right? So they have to go through long distances. Cellular transmission again at watts, okay, of power consumption. But if you are only doing a Bluetooth transmission across this room over meters, you are probably going to be transmitting at a milliwatt of power. So huge gap. And now amplifiers have their own inefficiency. So to pump out a milliwatt, you have to transmit. Obviously, you have to consume obviously a larger amount of energy, but still a larger amount of power. But still, this doesn't dominate. What begins to dominate though is the electronic component. So the electronic components depends upon two main things: the speed at which you are transmitting the data. So if you have a radio which is capable of which sends out symbols at 10 megabit per second versus something which sends out at kilobit per second, that will differ. And the other thing is the complexity of modulation. By that I mean the modulation complexity is affected by, again, the rate, but also how robust it is, because the decoding algorithms, if they put in more work, if you do more coding, things can increase. So this begins to dominate, and oftentimes, very easily you encounter situations where the receive electronic is greater than the sum of the two transmit entities, the amplifier and the electronics. So in a situation like that, now think an application like this. So if I have a network of sensor nodes which kind of send data from one to other to before it reaches the base station, then those little sensor nodes, for them to receive these asynchronous events to forward it, they have to stay up all the time because they don't know when this thing will arrive, or do they? And that's the thing. Can we design things so that we can handle rare events and still make some sort of a promise on the latency that we are going to see? So one way you can think of MAC protocols is that MAC protocols are the schedulers for communication systems. They play exactly the same role that schedulers and operating systems play, and same kind of issues and all sort of come up, except that the story from underlying hardware perspective is a lot more complicated. So the issue that comes up is the following: if nodes are not synchronized in time, if they don't have, so the extreme case would be nodes have no concept of any, not only the time but even the frequencies of each other. That I have an oscillator which has some frequency, you have some oscillator, some frequency. We don't even know that, so we cannot even talk about oh, we'll wait for a second or we'll wait for so many cycles. It has no correspondence. But that is essentially a setting which too extreme. So the more common case is that you have nodes, they have clocks, you know their frequencies because the manufacturer data sheets tell you that, you know how much ppms they are and stuff like that. What you don't know is that you don't want to pay the penalty of synchronization. So what might happen now is the following, that the A, which is our transmitter, wakes up once in a while to process the target, and then when it has an event to send, it sends out the event. So there is a packet which it is sending out at this point. Meanwhile, the receiver side, and remember A is also a receiver, as is B, so they are waiting to hear packets from other parties. So their strategy is the following. They say, look, I'm not, instead of staying up all the time and wasting, burning power, just waiting to receive something, we're going to wake up once in a while on a periodic basis, and if there is some packet being sent, we're going to receive it. Okay, so we are just sampling the channel to see if someone is sending a packet. Now, the problem, of course, with this very simple scheme is that the probability that this transmission will actually overlap with the reception side is extremely low, particularly if the receiver is being energy conscious, because for receiver to be energy conscious, it is going to have a long period and it's going to sample for only a short amount of time. Because if it samples for a long period of time, then energy consumption goes up, and if the period is short, average energy consumption will go up. So the bottleneck out here is that we would like to avoid the cost that we would otherwise incur to keep the reception times synchronized. To keep the time synchronized. If these guys had time synchronized, then A will know when B will be listening, and then A can transmit the packet precisely at that time. But we want to avoid that possibility. So the strategy then becomes that somehow we need to get the two parties to synchronize with each other. At the time, they need to exchange the packet, and not at other times. So they somehow we. So intuitively, it corresponds to, let's say, I try to call you on your phone, except that you are going to be checking your phone only once in a while. So whenever I call you, and if I know that you check your phone only every minute, then when I call you, then I should keep the phone ringing for at least a minute, so that you will check the phone during that period. So if I know that you check the phone every time delta, then whenever I'm calling, I should make sure that I keep the phone ringing for at least delta amount of time, so that you're bound to check during that period. And the only assumption now I'm making is that my concept of delta, or duration, is the same as your concept of delta duration. That means our frequencies are, that we have clocks which are frequency synchronized, or close enough, or we know each other's frequencies, but they're not time synchronized. So in case of data packets, the equivalent out there is the following. Whenever we send a packet, at the beginning of the packet, there is what is called as a preamble. And that preamble serves to have the receiver of a communication system learn the other party's clock frequency very precisely, so that they can sample the bits. I talked about that previously. So what these schemes then do is the following, that they send a packet with a long preamble. This is the equivalent of me calling you and letting the phone ring for a long period of time. Except, so one scheme could be, and this is from one of the earlier works in this case, the packet always has a long preamble. And that preamble is sized so that it is greater than the period. Okay, so then the idea is that irrespective of whenever the transmitter is sending the packet, the receiver is sometime during this time is going to wake up, because it checks every time t, and then the receiver, what it will do is it will keep waiting for the preamble to finish, and then it will ingest the payload. Okay, so traditionally packets would have had a minimal size preamble, just sufficient to train the clock enough so that the entire packet can be successfully received. But now we are going to have a long preamble to bypass this clock uncertainty, so that now this size of this preamble has to budget for a bunch of different things. So Firstly, it has to be longer than the period, as I said. It should also be period plus whatever is the minimal preamble size that is needed for successful communication. And that is because if the receiver wakes up just towards the end of the preamble, we still want to make sure that it sees enough of the preamble. We'll probably have to also budget for errors in frequency. So if we know that two clocks, our clocks frequencies may be somewhat apart, then I have to again budget for that time also. So we still have to play all of that. Now, this looks awful, that we are sending out this huge packet. But it's not all that bad. Why is that? What about our application basically says, look, I mean, yeah, I've suddenly bloated up the preamble orders of magnitude potentially, but I'm saying that this is fine.
Maybe because I'm not able to know some preamble on these pizza nuts.
No. Something much more basic. It's a rare event. It's happening rarely, right? So the transmitting is not happening that often. Remember, the setting out here now is that we are doing some sort of a rare event, and the problem we are trying to avoid is that in a normal system, the receiver would have to just stay up and listen for this rare event to arrive, okay? And at the same time, by definition, it's a rare and asynchronous event, so we don't know when it's going to come. So what we are trying to do is strike a balance. So certainly in this scheme, the cost of transmitting a packet has gone up, but the benefits overall are significant because the receiver is staying up for a very short period of time. So if we somehow had, obviously, best situation for us would have been if the two parties knew each other's time, and then they'll wake up at a designated time and then send out the minimal sized packet. That would be the best situation. But the problem there is that we'll have to somehow figure out a way to have the two clocks be synchronized. So now we are left with this trade-off. We can either say that the nodes don't need to synchronize in time, but when I do send a packet, I pay a penalty. Or nodes are synchronized and we are paying that penalty all the time of keeping things synchronous, but when the rare packet does happen, then I'm doing it very efficiently. And that balance, of course, depends on the system. As you might imagine, if packets are going out very rarely, then not bothering to synchronize is going to be the preferred scheme. On the other hand, if my clocks are really bad in terms of frequency, they drift apart a lot, then maybe this might become non-sustainable also. On the other hand, if packets are going quite frequently, then I can make use of those packets themselves to keep synchronizing. So that synchronization comes for free. We'll see later on, essentially, to synchronize clocks, we really have two schemes. One is we synchronize by exchanging message, or the other is that there is some sort of an infrastructure like GPS which advertises the time and we all get to know the time to some degree of accuracy. In either case, knowing time requires energy. Okay, either we have to have a GPS receiver or some sort of a receiver, or we need to exchange messages. Okay, so this thing works great. Where if the actual data exchange is going to happen relatively rarely, and the only assumption we are making now is we are basically saying that look, clocks need to know their nodes need to know their frequencies reasonably well, so that when this A sizes the preamble to be greater than the period, he knows what B's period truly is. So he knows B's period in terms of A's local clock. So that's another way of saying that the frequencies are known to each other. There's a variant of this which works somewhat better, and the way that works is instead of having this long preamble, what we do is we send the same packet multiple times, but with the minimal sized preamble. Okay, so we just repeat the packet a bunch of times, and the idea is that one of them will be heard by the receiver because we are sending enough of them in a train. And actually, you can optimize things further within this. In some schemes, what they do is they leave a little gap between these periods. And the idea is that if the receiver receives the packet, then it immediately sends out an acknowledgement, and then the transmitter doesn't need to send out subsequent part. So on an average, we say half half the number of packets. So these are the asynchronous schemes, and they, as you can see, seek to optimize for overall power, but particularly the receiver side power consumption goes down quite a bit. Now, the other scheme would be to do synchronization. So in the synchronous variant, we would somehow have the approach that each side knows each other time, so their times are aligned. So if there is some sort of a slot, they know the global time within the network, and then when node A needs to transmit to B, then it knows when node B will next going to be up, and it will transmit right at that time. So what happens in that case is that we'll still send a packet and we'll send a preamble, and the preamble has to be big enough to make sure that any uncertainty in our time synchronization is covered by it also. So again, we need a certain size of preamble just for the act of communication, because the way our communication receivers work is that since they are physically separate, they don't have a common clock. So for the receiver to sample the bits at the middle, so imagine like the bits are coming in time, we have to sample the bits in the middle, so the clocks have to synchronize. And when in communication courses you hear the term synchronization, that's what they mean. They basically say that receiver learns the clock frequency of the transmitter and then adjusts its frequency. And usually the clocks which are used in radio receivers have a little bit of ability to adjust the frequency by applying a voltage. So they are voltage control oscillators. So you can adjust the frequency by some amount. And kind of the idea is that nominally they use crystals which have the right frequency, and the adjustment is just to take care of any manufacturing and temperature variation. They are not meant for huge differences in the frequencies. But in this scheme, what's happening is we are once in a while we are synchronizing the time. And now when it actually comes time to send the preamble, I need to make sure that my preamble is large enough so that any incorrectness I had, any incorrectness in A's knowledge of when B will start listening gets covered. So the agreement is B will listen at 5 p.m. But last time they synchronized was some time ago. So between then and 5 p.m., by the time A thinks it's 5 p.m., the time at B may be some plus minus delta, and therefore A has to start transmitting somewhat earlier by just having a longer preamble. So that's all that's going on here. Now, the idea in this scheme is that every so often the nodes will synchronize. So that is shown by this kind of a beacon out here. So the idea is that they wake up on a periodic basis and do some sort of packet exchange to synchronize. And if a data packet gets sent anyway, we can use it for synchrony also, because every opportunity to send a packet or exchange a message is also an opportunity to synchronize clocks. Now, if no data is going out, then what would happen is that the actual synchronization messages are going to be exchanged on a periodic, on potentially large amounts of time apart. So what you're seeing in this particular diagram is that nodes wake up at designated times, but once in a while on those designated times, even if there is no data to send, they actually send some sort of a packet to get time, knowledge of time. So in case of Wi-Fi access points, what happens is that there is a time interval, and there is a special packet, a beacon packet, which goes out from the access point. It basically serves a couple of purposes. Number one, that beacon packet is coming periodically, and the other thing is coming at designated times, and it contains time information. It basically says time at access point is whatever, some t, and then all the receivers adjust their clocks, because the receivers know that that packet should have come at a particular time, but according to the receiver's local clocks, other normal nodes local clocks, but it would be arriving at potentially some different time because of clock drifts, so they adjust the clocks. So in this case, these dark blue things are the times at which we are actually sending some sort of a time information, and in a ad hoc network where there is no base station, usually some node will play that role of being the master, and that responsibility may rotate around. These episodes where we just see kind of a wake up thing, no information is being exchanged. So in typical protocols, you would find that synchronization itself, they potentially do at maybe 10, 15, 30 seconds, something like that. But the actual time TDM interval might be a lot shorter. But most of those TDM intervals, we just wake up, see if there is a beacon coming. If not, just go down to sleep, or not even wake up if you know that there was nothing going to be there. But once in a while, you do this actual handshake to correct for any errors in time that would have built up. So this is the synchronous model. Now, in both of these cases, as you see, ultimately we are limited by how good our clocks are, because in one case we are paying for it in the form of size of the preamble or number of packets we are transmitting, and in this case again we are paying for it in the size of the preamble. So fundamentally, energy efficiency in communication, one of the limiting factors is how good your clocks are. So last lecture, or I think maybe the lecture before, I mentioned those chip scale atomic clocks, and that came out of a program funded that was created by US DoD, part of DoD called DARPA, Defense Advanced Research Project Agency, and the sole motivation for that program was this application. Okay, so in military settings, you have soldiers carrying mobile thingies, and they have all these sensors. They call them UGS, unattended ground sensors, and they are supposed that they have to last for a long time because, again, if you read up on that, the constraints, besides food, the other big logistical item, non-weapon related logistical item for DoD is batteries, keeping batteries out in the front, because so many of the devices depend upon that. So anything which can enhance the lifetime is very useful. So chip scale atomic clocks go to the heart of this problem, which is you wake up, they are so stable that in theory you don't need any preamble at all. You can just start squirting out the bits, the header, the address, and also no training needed either, because the frequencies are so stable. So that was kind of the idea. The power consumption of chip scale atomic clocks, as I had mentioned, is around 75 milliwatts. So of course this is not good for our little sensors, because they themselves only take maybe 5-10 milliwatts. So I cannot afford to have a clock which is 75 milliwatt. But once you start looking at somewhat larger sized stuff, or things which are meant to go for mile, 2 mile type ranges, then 75 milliwatt becomes net energy winner. So errors in synchronization fundamentally then, or errors in, so let's back up. Stability of clock limits synchronization, and limits in synchronization affect the energy consumed by communication systems. And so time and energy in that regard are very closely coupled. If you improve the knowledge of time, then you can improve the energy efficiency of your communication quite significantly. So there's been some work, Prabal Dutta at Michigan, when he was at Berkeley, published kind of this nice paper showing that what is this fundamental limit, and kind of some simple algebra kind of leads to that. But the main thing is the following, that if you use standard crystals that you find, 50 ppm type quartz crystal oscillators, then your ability to duty cycle is kind of limited to 1 in 100, 0.01%. Okay, so 1 in 10,000. You cannot go any lower. Okay, so there is a lower bound on how efficient you can get energy-wise, which comes from clock. Now there are many instances in which your traffic is even lower. Okay, so these are systems which need. If I have something which needs to send a packet a day, right? And the packet itself may be, let's say, a few milliseconds. A day has 86,400 seconds, so you're already talking about 1 in 10 to the power 5. So from an application perspective, you could get away with a lower duty cycle, but your clocks become a bottleneck in that case. Okay, so and there are many other situations like this, like when there are systems deployed out, and once in a while they just need to connect back saying, hey, everything is okay. And then of course when there is an event, they want to send that event out very, very rapidly, very quickly. Okay, so a lot of military systems, space systems, they kind of tend to be in that category, or anything which is monitoring areas, seismics networks, same story. There are many parts of the planet, they have these distributed seismic sensors. Again, they operate off solar panels, things like that, but energy is an issue, and they don't need to communicate all the time other than this, hey, I'm okay, health status, and then when a quake is detected, rapidly send that event out so that rest of the infrastructure can react to it. So many applications fall into this category of rare asynchronous. So summarize this thing. There are several important use cases of time, synchronization, communication being one of that, energy sensitive communication, sensing being other. I didn't talk about it, but security type stuff falls into this category also. And also lots of things where you have to do very coordinated sets of actions. I think in one of the slides I had a URL to a pretty nice YouTube video which kind of shows multiple robots very rapidly kind of coordinating with each other. And the thing is, even a tiny bit of synchronization error means the object you are manipulating gets crushed or destroyed. Okay, so time sync sort of plays an important role in those things. Lately, one of the applications where, which is really exercising measurement of time quite a lot, is indoor localization. So GPS, as you know, works by measuring time of flight, but GPS operates over distances from satellite to ground, which are quite quite substantial. So even at speed of light, it takes significant amount of time for a signal to come down. But indoor localization, we are talking about potentially things which are tens of meters apart or even closer, and we need accuracies which are down to a meter or so. So let's say we want to localize within this room the distance between me and one of you. Okay, so we are probably 5 meters apart. That translates into, so let's see, speed of light is 0.3 meter per second. So a meter is 3 nanoseconds. So if we are 5 meters apart, that's 15 nanosecond. If I need an accuracy of a meter or so, so then we are basically talking about that I need to be able to measure times of 15 nanoseconds. So right there means I need to have a significantly fast clock, and I need to have errors, need to be able to resolve things down to 3 nanoseconds, so which means I need a pretty good stable sort of clock, and all the software issues and all. We cannot just make a system call and measure 3 nanoseconds. It has to be done better. Lately, several technologies have emerged, or standards have emerged, which are trying to do localization indoor by measuring the transmission of radio signals, as opposed to a slower signal like sound and all, which have historically been used. Some of the emerging, like the latest Wi-Fi standard, has this capability also. And the other traditional technology in this space has been radio signal strength, but that tends to be very flaky in terms of accuracy. So time of flight ranging has become a big driver. Some other interesting applications. So some people are working on the following application, which is pretty interesting. There are many services or systems whose security depends upon them knowing that you are within a certain distance away. Okay, so imagine the following kind of situation. I'm sitting out here, I have my car key in my pocket. Of course, therefore, my car doesn't won't open even if I press this, right? But what if you were to create a tunnel where there is one radio near my car in parking lot 9 and a radio out here, and then you basically relay the signals that would go back and forth. Okay, so presumably what is happening is my car is periodically checking for, is the key nearby, is the key nearby. You grab that packet, just literally relay it out here, retransmit it. My key will think that the car is nearby, will respond, and if somehow you get me to press the key or fake my key, you can transfer. So the idea is then, can we design systems which know that two parties are no more than a certain distance apart? It is called secure ranging and secure localization. Turns out the security of those systems depend upon very finely being able to measure time and kind of localize. A group down at UT Austin, they have been showing attacks on GPS where they fool your devices, even military-grade GPSs, into thinking that they're on a different part than what they really are. And what they do is they kind of fake the GPS signals. And a lot of that, again, depends upon, or combating those things depend again on timing technology. So there are a lot of security-related stuff which falls into this category. So hopefully, sort of I've given you sufficient belief in that, yeah, time plays a pretty critical role in a lot of these systems. Okay, so then as we talked about with clocks, a lot of those issues about how good we know the time between two nodes apply here also. So just like we had quality metrics associated with the clocks, you can talk about quality metrics being associated with a synchronization system. What's the maximum error? How long do we need to remain synchronized for? What is the space over which we need to be synchronized for? It's much easier to synchronize things down to nanosecond in a building than to a nanosecond over a campus. So larger the area, the harder it becomes. How much power and time you are willing to pay for it. So by that I mean how much energy you are willing to pump in for synchronization, and also how rapidly do you need to think. So GPS is great, but GPS has, among other things, there's one other problem GPS has is, from a cold start, it has to first lock to the satellites, and that can take tens of seconds in the worst case, okay? And they do all sort of tricks to sort of mitigate that, but still it takes a substantive amount of time. So a lot of these factors kind of end up dictating whether a particular synchronization method is good for your particular application or not. So sources of error. So of course, all the sources that we talked about for clocks themselves are applicable out here, because in between message exchanges or in between getting that signal from the GPS, you have to maintain time locally, and therefore you'll have some sort of a local clock which you are disciplining, but otherwise you're relying on that. So its characteristics matter. But then there are other things. For example, what's the resynchronization rate? How often are we resynchronizing? How often am I getting GPS to do that 1 PPS signal? If you think about, if I create a system where GPS is always up, keeps giving me that 50 nanosecond accuracy signal every second, firstly, it's probably an overkill, but the other part is keeping the GPS receiver up. You're probably going to be paying a watt or so on a sustained basis. Probably not a good idea. You might as well then buy one of those chip scale atomic clocks and burn only 75 milliwatt on a sustained basis. What are the network characteristics during the synchronization? We'll see later on that plays an important role. If the network delays are very flaky, then that creates a problem in synchronization accuracy. What are the computational latencies? For any synchronization to happen, we're presumably going to look at each other's clock values and all, and we're going to run some algorithms, their latencies and all. For example, let's say we exchange some message, but if it takes me an hour to process and figure out what your clock offset was, by the time I'm done computing, that knowledge is obsolete anyway. So these delays begin to matter. The delay in actual communication, the delay in computing, interrupts propagating up to your computation, things like that. And then finally, time stamping accuracy. A lot of this stuff depends upon essentially sending out packets which are timestamped. So I'm going to send you a packet and I'm going to tell you when I sent the packet, the time was this at my clock. And then you are going to get the packet and you'll say, when I received the packet, the time was something else according to your clock. And we're going to exchange this information and somehow algorithmically figure out how far apart our clocks were, how far apart our frequencies are by looking multiple of these exchanges. So all of these things add up to providing to result in some source of error. So when it comes to providing knowledge, providing time information to nodes which are distributed spatially, there are a bunch of technologies, and I guess I didn't list one, but I'm going to talk about it. So one, of course, which I mentioned already, GPS. So GPS fundamentally is able to give you most GPS boards that you can buy. They have they have this pin called PPS pin. On that pin, a transition occurs every second, and it has a stability of 50 nanosecond. So relative to the atomic clocks, which in turn are synchronized to UTC. So essentially, anywhere on the planet, as long as you can see the satellites, you can get time pretty accurately. But the qualifier is that you have to be able to see the satellites, which means not indoors, not underground, not underwater. NTP has been the workhorse of time synchronization on internet and local area networks, and it basically gives you several milliseconds of synchronization accuracy. I would say it's order of a few milliseconds over a local area network, order of millisecond, let's say, and order of maybe 50 to 100 millisecond if you are on the wide internet. And you can test for this thing. I mean, you take a couple of your laptops, which are all supposedly synchronizing over NTP, and you can kind of start comparing how accurately they are synchronized. NTP also has a lot of other issues. It takes time for it to synchronize, and the reason is that we have, I guess at this stage, hundreds of millions, if not billions, of hosts of different types on the internet, and to keep the load on the time servers manageable, it's not as if they keep bombarding the time servers at a very rapid rate, okay, but because the whole timing infrastructure will crash, the servers will be too loaded. So the way it works is that when the host starts, it takes it some time, perhaps few hours, maybe days, before it reaches the accuracy that we are promising, okay. So in the initial phases, have some rough time and then gradually stabilizes. And all of that happens. IEEE 1588 is a standard which is around 10 dozen years old. It's called Precision Time Protocol, and its aim is different. It aims at getting things which are in a relatively local area. So like, let's say, Disneyland or campus or an organization, they being synchronized. And what it aims for is sub-microsecond type synchronization accuracy. By the way, I mentioned Disneyland not out of just randomly. Actually, Disneyland, all the rides and all, they're all time synchronized. They run the whole thing on a tightly time synchronized network, and the motion of everything and all is script synchronized down to a frame rate which is on the order of a few milliseconds. Okay, so they're one of the long-running example of a tightly time synced kind of thing, because they have just way too many things going on. As you might imagine, a lot of their exhibits and all depend upon things happening at the right time. So time sync plays a pretty crucial role out there. Special time stamping hardware is used out here. So in NTP, what happens is when the packet is going out and I'm time stamping it, it's done in software. So there's some NTP software running in the user space. It sends out a packet and it consults the clock and says this is the time. Whereas in 1588, the Ethernet card itself or the Wi-Fi card itself or whatever other network interface card, it has time stamping hardware. And what it does is, as the packet is going out, it examines when a particular byte was sent, let's say at the end of the packet or the first byte of the header, something like that, and then it captures that timestamp. So it's all done in hardware, and therefore it's down to now very precise. And particularly if you're looking at like modern Ethernet cards in servers are operating at 10 gigabit per second. Soon it would be 50 to 100 gigabit per second. So the rates are enormously high. So software timestamping is just way too inaccurate. Another actually big customer of 1588 is the financial industry. Anyone thinks why? Knows why? Why might that be? Why would they need this kind of insane time synchronization? Yeah, what obviously stock market. What about stock market? Well, I mean that just asks for rapidity.
Like the order of transactions must be accurate across different.
Yeah. So who cares about it?
Investors.
Nope. Well, investors out of fairness, but investors get cheated anyway. It's the regulatory agencies. When something goes bad, then they have to do the forensics. Okay, so then they are trying to detect which trade happened when. Okay, and the trades, algorithmic trading is happening at such rapid speeds. I'm sure you have probably read about these things, that how they put their servers to be as close to the exchange and things like that. But when some episode happens, then they have to diagnose this thing. So the regulatory agencies. So in EU, they have mandated this, and I think in the US also, that all the transactions have to be time-stamped down to sub-microsecond accuracy. I guess EU initially wanted some 10 nanosecond type accuracy, which is essentially technically impossible right now. So all trades relative to UTC have to be time-stamped so that when they're audited, that can be done. So 158, if you look at companies which sell 1588 equipment, they so clearly target the finance industry. And of course, the other one is the whole factory automation. Those are the big ones. So 1588 or PTP is sub-microsecond synchronization accuracy. When I talk about it later, it seems that currently the bottleneck in what 1588 can do is the asymmetry in delays in the Ethernet cable itself. So let me explain that. When you take a run of, let's say, 100-meter long Ethernet cable, the speed of light delay, the signal transmission delay in either direction would be different. And typical Ethernet runs in a typical size building may have the asymmetry of delays, which is as much as 50 nanosecond or more. So, and that becomes the bottleneck. Asymmetry in delay is actually a problem when it comes to how well you can synchronize. In wireless, there are many systems in play, but from a research perspective, some work out of Vanderbilt University in Tennessee, it's usually the most widely cited one, although there have been some evolution since, but the basic, foundation was led by that work. It's called FTSP, or Flooding Time Synchronization Protocol. We are going to see that, but basically the way it works is there's a master, it sends out a beacon, the beacon goes to nodes which are one hop away, they in turn send it out to the next hop, and so on and so forth. But throughout, as the packets are flowing, a very careful accounting of delay is done on how much delay went over the wireless link and how much delay went into at each node. So both in NTP and 1588 and FTSP, the challenge that comes is the following, that we are trying to synchronize nodes which are not necessarily talking to each other directly, as in just over a piece of wire or a piece of radio link. They are talking through other nodes, through switches, routers, other sort of relays. So when I send you a packet, there is obviously some variation in delay, as I talked about, just over the wire itself, because propagation speed is variable. But then there is queuing delay, and then these intermediate nodes, between the time they receive and then they send out the packet, they may hold on to it for variable amount of time, depending upon what else they were doing. And so the end-to-end delay is subject to all these uncertain intermediate components. In 1588 and FTSP, the way they get around is that they require that the intermediate nodes timestamp when the packet came in, timestamp when the packet goes out, take that delta and subtract it from the timestamp which is being carried in the packet. So essentially, by the time the packet reaches the eventual destination, it actually has a complete accounting of how much time was spent just sort of idling or being grabbed by these intermediate nodes. And then you can get a better estimate of end-to-end delay. Whereas NTP doesn't do that. So in case of NTP, the delays that you see, if there were routers, galores of them, I mean through your ISP and your organization and all, each one of them is adding some delay, and those delays are all uncertain. So when you buy switches or routers which say they are 1588 compliant, what they actually are doing is they're timestamping and doing that adjustment along the way. FTSP was more of a specialized system done in an academic setting, but they basically had the same kind of concept. So careful accounting of delays is what in part is kind of needed. Okay, so now let's look at how some of these time synchronization things work out in practice. So the most so one thing to realize, a point which I had said, this is a slide I had shown earlier in the previous slide deck also. Synchronization doesn't necessarily mean we all need to agree upon a global physical time that we all need to synchronize with UTC, for example. There are many different notions of synchronization, and they may be adequate given your application. And the loosest form, and perhaps among the earliest work in computer science when it comes to clocks and synchronization, is simply the concept of logical clock. So all we care about is that we get the ordering right. So if an event happened, if I say that if I timestamp an event and you timestamp another event, then we will say that our clocks are synchronized if the timestamp I gave to my event and the timestamp you gave to your event are in order of their actual occurrence. Okay, so in this case, what's happening is I have a bunch of nodes in a network, 3 processors, and there are events happening there. And some of these events are message send and message receive. So E24 and E12 are the sending and reception of the same message. So looking at this, there are 2 types of constraints that we can see on the events. Firstly, events at a given node. Of course, we know their ordering. So at P1, E13 is after E12, and E12 is after E11 because it's a local thing. Presumably, it has a clock. It's timestamping it, so that part is okay. Then the other source of ordering is the messages. So E13 and E34 are the sending and reception of events of the same message, and therefore it stands to reason that whatever timestamp we give to E34, according to a global, if P3 were to do that, and whatever timestamp P1 gives to E13, they should, if we say that the times are globally consistent, then the timestamp for E34 should be greater than that of E13. Okay, so these are kind of 2 constraints, and if we obey that, then we can say that our clocks are consistent. There's a global synchrony that is happening. In particular, what it means is that if I look at, let's say, E32, and if I look at E25, we really cannot say anything about them. Okay, in the sense E32 is perfectly okay in this sense of synchronization if E32's timestamp is less than that of 25 or greater than that of 25, because we really cannot say anything about their ordering. This, of course, is not always a satisfactory thing, and in fact, in most applications, so couple of points. Number one, if I had physical time synchronization through, let's say, GPS, which was perfectly accurate, then logical clocks fall out of it automatically. If on the other hand I don't, the hope is that perhaps some protocol can give me this logical consistency and would be lighter weight than a protocol which would require physical time being consistent. So the way this thing works is, and this is very old paper, I think late 70s or early 80s, by Leslie Lamport, who's one of the Turing Award winners, so kind of very well known in distributed computing, clocks, and things like that. So the way it works is the following. We are seeking a logical clock, and we will be time stamping events according to that. And the idea is that we would like to stamp the logical clock to be such that it satisfies causality requirements. So based upon what I said a few minutes ago, we will go by the intuitive notions of ordering that such a system has. So we'll basically say that we have achieved synchrony if according to our clock, we will have timestamps in the same order as the order in which the events happen. So if we don't have physical clocks, then events at a node are in sequence. That we know because just from the program ordering, we can say, so all we can have is a counter, and every time we have an event, we use that as my local time and increment the counter. Okay, so that alone, I don't even need any physical clock to make that happen. If sending and receiving are events, then basically what we are saying is that we are defining kind of an ordering relationship, and we are saying that if A and B are events in the same node and A comes before B, we represent it like this. If A is the sending event of a packet and B is the receipt of the same packet by another node, then again A comes before B. And then, of course, a transitive relationship holds true. If A comes before B, B comes before C, then A comes before C. Furthermore, if according to this, A is before B and B is before A, both are true, then that means they are concurrent. Okay. So in effect, what we have defined is a relationship that A precedes B, or A causes B, whichever way you want to look at it. And then the implementation is relatively easy. So we want to find a way to assign time to these events. So time is nothing but a number. So what we'll do is for each node, we'll say that there's a local clock, just a counter. Okay. And then what we will do is whenever that node sees an event, whatever type, sending a message, receiving a packet, or some other event, what it will do is it will assign a timestamp to that event by consulting its local clock. So it will go to the local clock, whatever time it is, it's going to assign that. Then this whole system is represented by some function, and kind of the idea is that we are going to timestamp. We are going to say that if I have an event B, then the timestamp of that event is the timestamp according to the local clock of the node at which it occurs. So our goal is now that we are going to synchronize all these clocks in a manner that this way of assigning things, okay, that to timestamp an event, we just look at the local counter, timestamp it, and we are going to make sure that these counters at different nodes are operating in a manner that meets our requirement of synchronization. So, we have already defined what it is, okay? So the way for things to be synchronized according to this, a couple of conditions need to go through. We have to make sure that if A and B are nodes, are events in the same node, then Ci of A, that is timestamp of A according to clock I, is less than timestamp of B. So that's trivial to do. All we have to do is that every time an event occurs, we increment Ci. Okay, so if A occurs at node I, we timestamp A and we increment the counter so that the next event at that node will have a higher value. Second one is trickier. We also want to make sure that if A is sending event at some node I and B is the received event at some other node J, then we have to make sure that timestamp that I gave to A is less than the timestamp that J gave to B, because that is another way of saying is that I'm timestamping according to the global clock. And to meet this one, the approach is simple. What we'll do is when A is sending the message, when I is sending the message, then it will also include the timestamp. So the message includes a timestamp according to about when it was sent according to the sender's clock. And what the receiver does is that it will assign to when it receives the message, it will assign to it a value which is greater than both its local clock and what the sending event timestamp was. So kind of the idea being, if the sender says I sent the message at time 10 according to sender's clock, and my clock says it's only time 8, then I'm going to advance my clock to 11 and give the timestamp of 11 to this event. So this way, clocks kind of gradually each catch up. Every time there's a message exchange, we have a synchrony. If on the other hand there is no message exchange, then or only a subset of nodes were exchanging messages, they will move ahead, but the other node will advance only according to the local clock. So basically, we advance the counter every time there is an event, and we advance the counter to greater than what to the max of both the sending event +1 and my clock +1. We advance that, assign that, and then advance the clock to that. And if you intuitively, it's kind of obvious that if you were to do these, then that consistency is going to maintain. So it's easy to implement. Now, of course, if I had physical time available through GPS and all, then that's an alternative way, because I can simply use my GPS clock to assign the time, and in that case, I will get the correct timestamp. So there is an external infrastructure which is then giving us the information. So it turns out that nowadays, over the past 3-4 years, people who work in distributed databases, particularly entities like Google and all, they've kind of realized that GPS timestamps is a very powerful source of information. The only problem with GPS is that when things go bad, you don't know they are going bad. Okay. Recently, as in around a couple of months ago, there was an episode where during software upgrade of one of the satellites, things had gone awry, and I think there was a few tenths of milliseconds of error in the GPS time in certain parts of the planet. And that, among other things, for example, had brought down BBC radio stations and things like that. And if you were localizing at the time, then your location error could have been as much as a few tens of miles. So things happen, and of course, since the satellite itself got compromised in that case, no one really had any knowledge unless you had an independent way of knowing the location. So these timing systems are not perfect. Bad things occasionally happen, and that can of course cause chaos if Google were to be solely relying on that. So they also put in mechanisms to detect something bad is happening. For example, you can imagine that my primary source could be GPS, but I also have PTP or NTP running, so that if things go bad, I have a redundant thing to kind of check again. But most of the time, I can just rely on the GPS and save on message exchanges and stuff like that. So there's a fair bit of sort of work happening around those concepts now. So for a number of years, it was let's rely on protocols alone, to now let's make use of this global localization infrastructure that exists. Okay, so as you might have imagined, GPS plays a very important role. One other thing to point out is, while I'm using GPS, I keep saying GPS, there are actually several systems now in place for a variety of reasons, but one of which is that at times of war, US they have the ability that they can turn off GPS coverage in certain parts. Okay, so they don't want the enemy to sort of have access to it. So of course, not every country wants to be therefore dependent on it. So China has its own, Russia has its own, Europe has its own, and I think India just started its own, which has coverage around India and a few hundred miles around it. So every country which has the technical prowess to do it, they are kind of basically creating their own GPS-like infrastructure. So some modern receivers that you buy, what they do is they look at all those satellites and get even better accuracy than what a single one can have. So that's kind of the other trend which is happening. I don't know. I think the European system is called Galileo. I don't know what anyone knows what the Chinese system is called. And video, okay, and the Indian one just I know they've shot the last satellite up just this month, and the Russian one is out there also. So several of these, okay, and US itself is in the process of going to the third generation of GPS, which will have better accuracy, more indoor penetration, and I think from some of the workshops and all I've attended, it seems like at least for military purposes, they are going to be down to millimeter type accuracies anywhere on the planet. Okay, so it's pretty amazing. Okay, so how does GPS work? We all hear about it, obviously, but just to give you a bit of an insight into what happens is, so loosely speaking, cluster of satellites out in the sky. They have atomic clocks which are synchronized, and not just synchronized in a traditional sense, but synchronized taking into account relativistic effects. So this is one example where relativity comes into play, because the speed at which these satellites are moving, you do have to account for those relativistic effects. The other thing is you need to know the location of the satellites accurately. So that comes from orbital mechanics, and again, because of wobbling of the Earth's axis and things like that, there are corrections which are continually applied. So there's a whole sort of infrastructure to make sure that the satellites themselves, they're synchronized and we know the position. And then what happens at the receiver is that there's a local oscillator at the receiver, and what it is doing is it's basically getting the messages from a bunch of satellites, at least 3 if all you care about is XY location and you know your height already, which in many applications you do, you know you're on the surface of the Earth. If you also need to know Z, then you need 4 satellites, and because of errors and all, you usually need a lot more, so many receivers go to dozen satellites or whatever, they track that many. So what's happening now is that there are 4 unknowns out here. Remember, this guy is not synchronized. It doesn't know the times out there. So all it has is a local notion of time. It doesn't know how much its clock is offset by. So it has 4 unknowns. It doesn't know its location, or in the special case, it knows its Z, it's on the ground, and it doesn't know the time. So it basically, the basic equations are very simple. Time of flight depends upon my unknown location and my unknown time, because I don't know the offset. So there are 4 things. You kind of create all the equations and solve for them. That's in very simple simple terms. Of course, lots of other complexities come into play out there. These signals, as they go through, they are subjected to all sort of impairments and things like that. The other issue is the local clock out here that drifts. So GPS is one of the cases where they use the costlier oscillators. So GPS in your phones and all, they use the TCXOs as opposed to ordinary crystal oscillators, because that directly affects the accuracy. And if you're willing to use the OCXOs, they're even better. So GPS gives you that's how it operates. Accuracy. From a timing perspective, I often said the PPS signal, so it's order of 50 nanosecond. Doesn't work indoors. If something goes bad, it may take a long time to recover. I guess the other con is that GPS was designed in the somewhat innocent days when hacking was not all that prevalent. So these signals which are sent by the satellites, they are not cryptographically signed. And what that means is that others can fake that signal. And that causes that can cause problems, and there have been plenty of episodes. And of course, as I'm mentioning, several groups have shown those attacks. The UT Austin one, which I mentioned, is probably the most visible one. And there have been some attacks which have been some years ago, I think 4 or 5 years ago, there was this episode of a US drone which had landed in Iran, and Iranians had captured it. And the leading theory, which may or may not be true, I've heard both versions, was that the way that attack works is that the drone was designed to use military version of GPS, which is cryptographically secured, but anything can be jammed. So the theory is that the Iranians, you jam the military signal, so then the fallback for the drone is to switch to civilian signal, and which, as I just mentioned, can be spoofed because it's not only it's not encrypted, it's not even signed. Okay, so anyone can send it, and so the drone then thought the fake transmitter is a real satellite, thought it was still over Afghanistan when it was actually in Iran, landed safely, got captured. And plenty of academic groups are showing this kind of work. It turns out that very gross forms of these attacks you can take care of. So like suddenly if I turned on a fake GPS satellite, then the receiver would say, hey, how come there are 2 satellites with the same signal? Okay, and then of course it will detect that, perhaps discard it. So the attack has to be mounted in a manner where the way it works is that you start out by creating a very low power signal which is matching perfectly the one of the correct satellite. Okay, so this means that you have to be close enough to the object you're trying to fool. And then you start gradually increasing your power so that the receiver remains locked, what it still thinks is a genuine satellite. And then once you have raised the power enough, then you start shifting away. By that I mean you start changing the phase of your signal. So now the receiver basically says, aha, this is a more powerful signal which is moving away. It thinks you are the real satellite, and then you gradually kind of move it out. So you have to mount these attacks in a manner that the receiver cannot simply discard you as a fake signal. Okay. Now, people do this kind of stuff. There are you can download software, run it on GNU Radio, and kind of create your own GPS spoofer. It's illegal, but you can. Okay. So back to the GPS. Part of the problem with GPS also is it's power hungry. And the other thing to note is that when I talk about GPS can provide you time, your typical like black box unit that you buy as like this is a GPS receiver, they only provide you time over a serial port. And the serial port adds a lot of delays and all. So we are not talking about that. It has to be GPS receivers that give you this PPS signal. But you can buy these things for, if you go to places which sell you the board as opposed to a Garmin GPS unit or something like that, which won't do that. Okay, so that's GPS. There are some other sources of very precise time which are very readily available also. I'm sure you have seen really very cheap wall clocks being sold as atomic clock accuracy, right? Have you seen these? I mean, you go to whatever, any run-of-the-mill store and they have these little timepieces and all, and they say atomic clock accuracy. How do they work? What are they doing? They don't have a GPS receiver. So I guess what I'm trying to say is think about what are the other sources of time that exist around us, which you can easily leverage off and at least create a reasonably accurate thing. So those guys are claiming all atomic clock accuracy.
You just connect to internet and get you just connect to internet.
No, they're not on the internet. But that could be, they could run NTP and do it, except that no one advertises NTP as atomic clock accuracy because it's not. So a couple of other sources of precise time and precise frequency. So firstly, let's talk about frequency. One very good source of very stable frequency are the TV stations. The NTSC signal which is sent out is from very stable clock sources. Okay, but that only gives you frequency, doesn't give you time. Another very good source of frequency are the cellular signals. Cellular towers have very precise clocks, in many cases now chip scale atomic clocks, because for the very same reason I was talking about with MAC protocols, they are orchestrating transmissions of different phones, and also if they were to get them orchestrated in time, that results in better bandwidth utilization. And the thing that AT&T or Verizon cares the most about is how many users they can pack into spectrum. So that's one other source. But the third very important source of time is something which many governments operate. What they do is take their atomic clocks and then they send out a signal over a regular radio station, okay, as essentially data being transmitted on that radio station. In the US, the federal agency which does this thing is called NIST, National Institutes of Standards and something. Their main setup is based in Colorado. So what they have is they continuously broadcast time and frequency signal at with a very high power on certain shortwave and medium wave type radio stations. So the carrier frequency of these radio signals gives you a very stable, atomic clock stable frequency standard, and the data which is modulated on that signal is carried are bits which are signifying year, time, amount of leap compensation, things like that, a whole bunch of things. So basically a very cheap radio receiver capable of listening to a standard AM radio type signal can then demodulate it and get the time. Okay. Now, and I've kind of described some details. So basically the time is in binary coded decimal. It is sent at 1 bit a second using pulse width modulation. So those are details, but the point is it's pretty simple, which is why it's built into these $10 bedside clocks and wall clocks. Okay. The way it works though is that you are going to be behind the clock in Colorado by whatever is the transmit time, because you have no way of knowing that. Now you can potentially you could do some level of compensation, like we know speed of light, if we know the distance, perhaps maybe you can provide a mechanism where you say feed in your location, do latitude, longitude, do the compensation, but even that doesn't necessarily work because the radio waves often bounce off the upper layers of the atmosphere. So the actual time to travel may be more than the sheer distance, but you can do some compensation. The other thing is you can begin to learn something about the path delay by observing the variations. So what I mean by that is I'm getting these signals and they're telling me the time. And meanwhile, I can measure the time gap between one signal and the next signal according to my local clock. And I know something about that too. Something about that. And if the signals are arriving through variable paths, I can begin to compensate for them because the shortest arrival would be the one which is along the most direct path. So that's kind of the basic concept. There are challenges with this because how much the signal propagates depends upon atmospheric conditions. So at different times of the day, footprint can be small or large. So sometimes the coverage, as you can see, reaches all the way to South America, and sometimes it's just over continental US. But the primary service region out here is the US, so that's what they seek to cater for. An advantage of this over GPS is that these are radio waves that can go indoors. So unlike GPS, which has higher frequency, so you need to be out in the open. The flip side though is that you're not compensating for this one directional delay. The same signal actually is also available over telephone lines. So you can kind of call a phone number and the data squirting out of it is this kind of data, which again you can design a acoustic decoder to get things out. The only thing is that the phone system has a longer delay because it goes through switches and routers and stuff like that. And if you're doing it over cellular, it would be even more, but you can again kind of do this. So this is a cheap way of doing things, and many embedded systems make use of it because the circuit is pretty simple, works indoors, but accuracy is obviously, because of these delay issues, the accuracy is worse. And the primary thing is because you're not trying to figure out your location. You're basically saying, the sender is saying time is X, I'm going to assume that's the time. And so it's more like the way Wi-Fi access points work, where access points say time is X, and everyone tunes to that. In case of Wi-Fi, it's fine. You're looking at delays which are sub-microsecond because it's a local area. In this case, the delays, coast-to-coast delay is 20 milliseconds. So you're looking at delays which are order of 10 millisecond. And so you're always behind by that much, depending upon your location. So why don't we simply put WWVB receiver or one of the other things? Outages, so oftentimes it's out for hours, environmental condition, rain, those sort of issues. So during that time, you're stuck with an uncompensated oscillator. And since it's being used in the cheap system, so the kind of oscillators you're probably going to find in your bedside clock or wall clock are very cheap. And in fact, in many super cheap design, they even don't even put an oscillator, they just work off the AC signal. So essentially, they are intermittently synchronized. And the other thing is they tend not to do many smart things, these systems. They will see, you might see kind of jumps happening, which are not very well done. But nevertheless, you can get accuracies which are pretty good. And the design of these kind of receivers, I mean, your receiver is always on, but nevertheless, it's much cheaper than a GPS type receiver. Next up, in terms of things which are ubiquitously around us, is AC signal. AC signal is all around us, and it actually leaks. So it's not simply that you have to actually connect to the wire line. You just put a spectrum analyzer with an antenna out here, you'll pick 60 hertz signals all the time. Actually, you'll pick a whole lot of other stuff too. You'll probably pick up the signals from your fluorescent lamps also. Okay, they have these electronic ballast which have a high frequency component. So there's all sort of frequencies around us. The AC signal frequency is of interest because power companies try to keep 60 hertz signal very stable. Why do they do that? So, okay, I have the bullet out there. So it used to be like if you had an isolated system, you can have a generator nominally 60 hertz, we are okay. The thing is now we have lots of power suppliers who connect to the grid, and if the frequencies differ, then you can have power flow occurring between generators, and that can begin to cause large power swings in the network, all sort of issues. So when a generator connects to the network, the goal is to keep it to an agreed upon 60 hertz. But what 60 hertz are we agreeing upon? There has to be a stable thing. So this is where, again, using the 60 hertz as defined by some standard is the one which we kind of which all of them do it. So the 60 hertz, they try to keep it very stable. There are websites where you can look at the instantaneous frequencies of the grid. I know UK has a very cute website where you see a needle, and for the entire UK grid, what is current frequency, and it's insanely stable. But when there are major load changes, like summer heat or something, then the frequency may start going down, and then they kind of bring more generators aboard to kind of bring it back up. But the point is that for a lot of purposes, it's good. It's short-term unstable, but long-term very stable. So there are people who have exploited that. And the nice thing about this is the cool application where I saw this one, this work out of CMU, is for coal mines and all. So there, neither GPS nor WWVB, those kind of things work. These are things which are hundreds of meters below Earth, but there is AC signal because electricity is being delivered. So they make use of that. Essentially, so this thing is kind of a little node, and it basically can run very low power consumption, but basically what it does is it picks up the AC signal from nearby AC wiring and uses that as a stable source of frequency, and then builds up a synchronization infrastructure on top of that. So this is another one. Yet another one is A2.11. I already mentioned that for MAC protocols it uses it, but this information is around us. So essentially, by listening to the beacon packets, you can acquire a very stable source of frequency, and in some cases time as well. So A2.11 in conceptually is a bit like the NIST system. That is, there's a transmitter sending things out. The only thing is that the distances here are very small, 100 meter. So the gap isn't that much. And finally, among the existing systems is the NTP Internet Synchronization System, which is the standard. And the way it kind of works is they have it's a tiered system. So at the bottom are regular computers. But then on top, there's a hierarchy of increasingly more accurate time servers. So I think they call them as sort of different strata. So at top level are servers which basically are a root of the system, atomic clocks, or something very precise like that. So they are synced to UTC. Oftentimes nowadays it's basically use a GPS for that purpose. Then they distribute time to the next tier, which in turn distribute time to the next tier, and then finally you get time there. In many cases, you can jump all of this and go directly out here, like I was saying last time, on our campus, time.ucla.edu is a stratum 1 server, and you can kind of connect to that, and as long as you're not obnoxious about bombarding it with too many requests, they will keep on. The reason we have this hierarchy is to balance out the load, because there are relatively few of these and they're expensive. So you kind of get one node on your LAN to sync up, and then everyone else syncs up to that in the LAN. That's kind of conceptually what happens. Now NTP sounds very simple, but it's actually an insanely complicated piece of code because it does all sorts of pretty fancy algorithms to not so its job is not simply what time it is and I'm going to adjust the time. Remember I also said earlier that we want to keep that load under control. We don't want to just keep consulting the time server every second or every few seconds. We do it once in a while, and in between we need to maintain good time. So what NTP also does is it learns what the characteristics of the local clock are. How was it frequency drifting? It uses pretty sophisticated control theory, signal processing type algorithms to learn a model of the clock, see how it drifts, and uses that to do the local time. So it essentially is learning the clock parameters. It also has to deal with the fact that some of these servers up there may actually not be behaving nicely. Either the server may be malicious, or the server may be down, or the path to the server may not be good. Maybe it's seeing enormous amount of delays. So another thing it does is it also tries to find outliers, things which may be currently be bad, and again discards them. It does weighting of different kind of samples and all. Upshot of all of this is that, oh, and by the way, it uses those PLL type structures that I described last time. Upshot of all of this is that it basically is trying to achieve three things really. One is robustness by making use of multiple servers. Second thing is keeping the network load low so that you are not continually bombarding. And the third thing is learning a model of the clock so that you can do things in between the synchronization episodes. And then once it does all of that, then it makes a call to a system call to Linux to adjust the clock. So Linux provides system call which lets programs adjust Linux's notion of time, which actually comes from Linux's notion of time is basically some counter which is doing a periodic interrupt according to some notional time we have set. Let's say 10 milliseconds. Every 10 milliseconds there is an interrupt, the counter gets updated. But that's 10 milliseconds according to the local clock. What NTP does is it basically provides the compensation factor and does the clock adjustment. on that. So very complicated thing. And by the way, NTP is not the only time synchronization protocol that exists. There is I think there's something called a simple NTP, which is kind of a lighter weight version of NTP suited for low end systems. Then of course there is precision time protocol PTP or 1588. So you can replace NTP by PTP and get more precise thing. Even low end embedded systems nowadays, some of them Linux types, they have support for PTP, so they can do timestamping at the hardware level. So NTP is not the only thing, but it's basically is by default there. All the major operating systems have it, and there are plenty of implementations that are available. You can make your computer to be an NTP client, but you can as easily make it to be an NTP server also. So at least Linux has that capability built in, and so do with some modest effort you can activate it on Mac and Windows also. Let's see. Internally, NTP also maintains information about how well it is doing. So it has a sense of what is its uncertainty. So I talked about quality of time before. So this is an example where NTP internally has that information. Not only it knows what time it is, but it also has a sense of what is the variance that it was seeing in it. It doesn't expose it, but you could imagine doing it, and then when you're time stamping something, you can budget for that uncertainty. So with some additional API support, NTP can help with that also. So main thing about NTP, then readily available, basically a standard. It's secure. It has authentication support, stuff like that. Stable to long-term stable, and gives you accuracies over a LAN, milliseconds, over wide area, tens of milliseconds. Not very flexible, so you cannot tell NTP that, hey, I need a higher accuracy, why don't you synchronize more often? Or no, I can get away with a cheaper accuracy, maybe you should relax. So the way it was designed is it's designed for running in the background at a constant low rate, independent of what the applications may need. Okay, it's a good or a bad. I mean, it's a trustworthy service always there, but it just operates at a fixed rate. So for example, it took it. This is from some paper. It took NTP an hour to reduce error to 60 microseconds on a local area kind of a setting by doing a polling of 16 seconds. So every 16 seconds, which is a lot. Okay, normally NTP server they contact NTP server maybe once a day or even less frequency. Not very energy friendly because it's kind of always running, but it's there. So you may recall this curve from last lecture also. So Allen deviation, this is NTP, this curve out here, and what you see is firstly it's around 3 to 4 order of magnitude inferior to GPS. But if you let NTP run for a long time, over long durations, it can give you a pretty stable source. Issue is that most of the time you're interested in somewhere in this regime, and if that's where you are better off with other sources. Okay, so why can't we just not use NTP or GPS? I hope that I have sort of presented the two sides. So GPS has issues, availability issues, certainly some security issues. Of course, its frequency is 1 PPS, so it cannot be the sole time. NTP, same story. So you still need local oscillators. GPS is power hungry, costly. There is also the slight issue that availability is under US government's control, not under you. NTP, by the way, has the same set of issues. It's just that it's more resilient because there are NTP servers all over the internet, so you can sort of connect. But if there is a wide area GPS disruption, quite likely a lot of these NTP servers will take a hit also, because the most common NTP server is basically working off GPS. But even with all of these, they are not always the best technology to put on every embedded node. NTP is usually way too inaccurate, and GPS is usually way too accurate or powerful. So something intermediate often gets needed, and we'll do that next time because we're close to the end. So there is a set of protocols and all which have developed, which are catering specifically to networks of embedded devices and all, and you'll find these things in kind of sensor networks, IoT devices, these kind of things and all, where your timing needs exceed the capability of NTP, but at the same time don't reach a level where you can afford to put GPS everywhere. PTP still isn't there in the wireless arena yet. So while you can buy PTP switches and all for your regular Ethernet, and they tend to be costly. I recently bought a PTP switch for my home, and it was around $600, whereas an equivalent Ethernet switch you can buy for, I don't know, $30. Okay, so all that stuff costs money. Still an evolving technology. So next lecture, just a reminder, is going to be on by my two students on Android OS architecture, and I'll see you guys on Thursday.